Hi, this is Physics Unit 1, January 2014. Let's start. Number 1. Which of the following is a correct statement? So we have weight, velocity, mass and force, and we have to identify whether they are base quantities or derived quantities. So basically a derived quantity is derived from a base quantity, right? So when we have weight, W equals to mg, m is the mass and g is the gravity. So mass and gravity are basically base quantities, and this weight is a derived quantity. This weight is derived from these two base quantities, right? So weight is a derived quantity. Velocity, so velocity is basically displacement by time, and we know that displacement is a base quantity, time is also a base quantity. Since displacement is in meters, right? Length is a base quantity, time is a base quantity, temperature is a base quantity. These are the base quantities, and derived quantities are those which are derived from two base quantities. So velocity is a derived quantity. So B is also not correct. Let us check C. C says that mass is a derived quantity. So we have F equals to ma or W equals to mg. We can clearly see that the gravity is a base quantity, mass is a base quantity, acceleration is a base quantity, mass is also a base quantity. The force and the weight are derived quantities. So C is also not the correct answer. Force, the part D says that force is a derived quantity. This is true because here we can see that F equals to ma. This F force is derived from the two base quantities, mass and acceleration. So the only correct answer to number 1 is D. Number 2. A ball launcher fires a ball horizontally off the edge of a lab bench. So it is being fired horizontally. So initially there is a horizontal component of the ball, but there are no vertical component initially. But when it is in the air, vertical component of the ball, of the velocity of the ball, increases to the gravitational acceleration. So basically when the ball is at this point, here we only have a horizontal component, and then the horizontal component just keeps decreasing a bit due to the air resistance, and the vertical component just keeps increasing because the vertical component is related to the gravitational pull of the earth. So basically it goes in this direction due to the initial horizontal component of the ball, and it goes down into the ground, towards the ground, due to gravitational pull. So which of the quantities is different for the two launches? A. Gravitational acceleration. So the gravitational acceleration is always constant since it is being conducted on earth, right? On a single lab bench. So the lab is on earth, it is not a moon, right? The two experiments, the two balls are in the same condition, the same gravitational acceleration. So this is the same. Time of flight. So basically the time of flight is really important. The thing is, we can use S equals to ut plus half at squared, right? Initially, if we just consider the vertical components, only the vertical components, initially the vertical component of the velocity is 0. So u is 0. So basically what we can write is S equals to half at squared. And since the gravitational acceleration is constant, this acceleration is constant, and since this height from the launch height to the ground is constant, this should also be constant, right? Since the displacement is constant and acceleration is also constant, the time of flight is also constant. So basically, even if the balls are launched at the same time but they have different paths, this ball will reach the ground and this ball will reach the ground at the same time. The range is different. The range is different for the two balls. B is also not correct. C is not correct because the launch angle is the same as we can see here. Initially it has just the horizontal velocity, since the question says that the ball is launched horizontally. So since it is horizontal, there is no vertical component, so the angle is just in the horizontal direction. If there was any vertical component, then resultant velocity would look something like this, not entirely horizontal but just towards the horizontal. So C is also not correct. D is correct because the initial velocity of, for example, this B is higher than the initial velocity of A. Since have S equals to d by t, the displacement equals to distance by time, we can say that the time is constant, right? The time of ball in the two balls in journey are constant, right? The time is constant, but the thing is the time is constant, but the distance, the horizontal distance is higher. Since for B, if we consider B, if the horizontal displacement is higher, this means that the speed for B was higher. The initial speed or velocity was higher. So basically for B, the launch angle was the same, the gravitational acceleration was the same, the time of flight was the same, but the initial horizontal velocity for B was higher than that of A. So the range, the horizontal distance covered was also high for the same time of flight. So the answer to this question is D. Number 3. A pendulum contains an 18 Newton weight attached to a piece of string. The weight is released from position as shown in the diagram. So this is released from here and it goes in this direction and goes up again. At this point, the velocity is again 0, and at this point, the velocity is maximum. So the speed in meter per second at the bottom of the swing is given by, okay, so maximum. So basically the thing is, here what's happening is the gravitational potential energy here is being converted into kinetic energy in this part. So basically gravitational potential energy, GPE, is equals to mgh, mass into gravity into height. So basically the height is 0.06, mass is 18 Newton weight. So basically what we have is W equals to mg. So mass is basically W by G, right? W by G, we have W by G, and so mass is W by G. So W by G into G into H. So basically these G cancel out, so WH, the GPE, is equals to weight into height. So what is the weight? Weight is 18 Newton into height is 0.06. So this gravitational potential energy is being converted into kinetic energy, right? The kinetic energy. So kinetic energy 18 into 0.06 is equals to half mv squared, right? Half mv squared, and that m, the value of m is W by G. So 18 by 9.81 into v squared, right? So these 18 and 18 cancels out. So we have 0.06 into 2 into 9.81 equals to v squared. So v would be equals to root over 0.06 into 2 into 9.81. So the answer to this question is C. Number 4. A pump is positioned at the bottom of the well and it pumps 15 kg of water 25 meter to the surface each minute. So basically we have a well here and we have a pump here, and this pump basically pumps the water at 25 meter above the surface from here to here, and the mass of the water is 15 kg. So what is the power of the pump? So power is basically work done by time, right, or any type of energy by time. In this scenario, the energy is being converted against gravitational potential energy. Their work is being done against gravity per unit time. So gravity is basically mgh by time. So what is the weight of the water? The weight of the water is 15, the gravity is 9.81, and the height is 25, and the time is in each minute, so 60 seconds. We always need to convert it into seconds, we do not keep it into minutes or hours. So basically this answer rounds to 61 watts. So the answer is B. So number 5, the velocity time graph of an object is shown. So basically the velocity goes from 0 to 3 meter per second in 6 seconds, and then it again accelerates. So here we have acceleration, and here we also have acceleration, but a lower acceleration as the gradient is lower at this point, and then there is deceleration, right? So these are the 3 points. So from this point to this point, higher acceleration, from this point to this point, lower acceleration, and then deceleration. The initial acceleration of the object is, so basically we have a velocity time graph, and we also know that acceleration is basically change in velocity by time, right? So change in velocity by time is actually the gradient of velocity by time graph. So the gradient of this graph up to this point is basically the change in y by change in x, right? So we have this coordinate 3, so we can write change in y is 3 and change in x is 6. So 3 by 6 is 0.5. So the answer for number 5 is B. Then we have number 6. Number 6 says that the displacement during the time of deceleration is. So basically the period of deceleration is this one, right? This is the period of deceleration, and we need to find the area under the graph of this. So basically what we have is the area under the graph. If we draw a line, we can see that this area is the area under the graph, right? So this is the displacement. So area under the graph is basically the area of this triangle, the area of this triangle. So the area of this triangle is half into base into height, right? So half into base is basically 12 to 19. So this is 19 minus 12 into height. So height is basically 4.2, right? 4.2. So 4.2. So we have the answer of 14.7 meters, which rounds off to 15 meters. So the displacement is C, and the displacement is not D because it is not a vector quantity. It is just a scalar quantity. If it was velocity, then the velocity might have been minus 15 or something like that, and the initial acceleration is positive here, right, in part B, but the deceleration would have been negative since the direction is opposite. But since this displacement of during the time of deceleration, this is constant, so basically this we have, for this one we have 15 meters. So the answer is C. So in the editing column, just keep the part C explanation, don't include the part D explanation. Number 7. A force of 15 Newton is applied to a wire of cross-sectional area 3.0 into 10 to the power minus 6. The wire extends by 1% of the original length. The Young modulus of the wire Newton per meter square can be found. So basically the Young modulus is basically the ratio of stress by strain, right? Stress by strain. But what is stress? Stress is basically force per unit area, and strain is extension by original length, right? So force, what is the force? Force is 15, and the area, the cross sectional area, is 3 into 10 to the power minus 6. And the extension, what is the extension? Extension is 1 out of 100, right? So if the original length is 100, the extension is 1. So extension is basically 1 and the original length is 100. So we can rearrange it and write it as 15 into 100 divided by 3 into 10 to the power minus 6. So 15 into 100 is basically 15 by 0.01 into 3 into 10 to the power minus 6. So the only answer that matches with this question 7, and the answer is B. Number 8. The main component of a Newton meter is a calibrated spring. So basically we have a spring here, and this spring, when it extends, we have 1 Newton, 2 Newton, 3, 4, 5, 6 and so on. These are calibrations, right? These are calibrations. So basically this is a calibrated spring. When it extends, when a force is applied, when we add a load here, this spring extends, and for example this bar goes to this. So here the reading might be this direction, so this might be 3.5 reading and so on. So basically this is a calibrated spring. The extension of the spring is calibrated, is shown in range with values. So the Newton meter is to be used over a greater range of forces. Which of the following should be increased to allow this? So ductility of the spring wire. So this is not correct, since ductile is basically a plastic deformation. If it has a ductile deformation, the spring would not return to its original length, and the limit of proportionality would be crossed. The force would not be proportional to extension, and thus the value shown on the graph would not be the correct answer. A is not correct. B, precision of the scale. So precision is basically we have the same scale and we will just use more divisions, right? More divisions like 0. 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2, 2.2, 2.4, 2.6, 2.8, something like that. So precision, we can increase the precision of the scale, but we won't get greater range of forces. For example, forces greater than 10, we won't get it if we just increase the precision. So part C says that stiffness of the wire, stiffness of the spring. This is correct because we can just use, for example, we have a spring here and we can just use a thicker spring like this. Basically what we will have here is, for example, if we apply 10 Newton here and 10 Newton here, the extension here would be 2 meter and extension here would be 5 meter. So this, for this spring we can calibrate it as, for example, till this length, or this spring up till this length, we can just, for the thicker string, more force is needed for any extension, right? So for less extension, this calibration might be 10 Newton, and for this spring, the thinner spring, this calibration would be 4 Newton, right? Like this. But when we are using a thicker string, more force is needed to provide the same extension, right? Since we have F equals to kx, if we increase the thickness of the spring, the value of k would increase. So what does this mean? The value of k is the spring constant, or the stiffness. So basically for the same force, if the value of the stiffness is increasing, for the same force applied, the extension would decrease. So we can calibrate this range according to the extension. So for example, as I have just said now, that for this spring 2 meter extension would mean 5 newtons, but for this spring 2 meter extension would mean 20 newtons. So we just need to adjust the stiffness of the spring and just it according to the stiffness, right? So C is the correct answer. Is that ultimate tensile strength of the spring? So this basically says that, for example, spring breaks after 100 newtons, right? But another spring breaks after applying 200 newtons. So basically the second spring has a higher ultimate tensile strength, but this does not affect the calibrated spring, since we need to calibrate this range. So part D is also not correct. Part D is also not correct. Another reason is part D involves plastic deformation. So we do not hope plastic deformation, since at that point the limit of proportionality has, and this is not proportional to extension at that point. So the only answer to number 8 is C. Number 9. Some masses are added to a piece of copper wire as shown. Measurements are taken of the length of the wire as the force on the wire is increased. So here we have a G clamp. The clamp is basically holding the wire in a fixed position, and we have a pulley here. So the pulley, the wire goes down like this on the pulley, and this is the holder and this is the mass. So this is it basically, and this is the force is basically increasing the length of the wire. So the work done in stretching the wire is given by the area under the graph and the area under which graph. So basically the area under the graph is basically half fx, right? Half is the numerical value, f is the force, and x is the extension. So basically half fx basically means that it is the area under the force extension graph, right? The force extension graph, if we have a graph like this, the graph just curves out. So the basically the area under the graph of, for example, force F1 is this, right? So the area under the graph is basically this. So the area under the graph of the force extension graph is basically the work done. So this is only applicable up to the limit of proportionality. The limit of proportionality is basically the point till which the line is a straight before it curves out, right? So the limit of proportionality is being obeyed in this area, right? In this area. So the only correct option is D, because in only D we have force and extension. Change in length is actually the extension. So the area under the force against extension is actually the work done in extending or stretching the wire. So the answer to question 9 is D. Number 10. In an experiment, a small metal ball is dropped into a cylinder of oil. So this is a cylinder and these are the oil. So the time taken for the ball to fall to the bottom of the cylinder is recorded. So basically, so if we draw a free body force diagram, we will have weight downwards and we will have drag upwards. So drag is basically equals to 6 pi nRV, right? Where 6 and pi are just values and n is the viscosity of the liquid, r is the radius of the ball, and v is the velocity of the ball. So higher the radius, so for example we have a ball of this of mass m and a higher radius, a bigger size of mass m, but the radius is greater, right? So the drag force for this ball, considering it has the same mass and the same velocity, it will have a greater drag force. This one will have a greater drag force because this one has a greater radius. So higher radius means higher drag. The experiment is repeated, which changes the ball would result in the greatest decrease in time it takes to reach the bottom of the cylinder. So what scenario would give us situation where the ball reaches the bottom of the cylinder the fastest? So basically we will have weight, right? So basically we will have weight. So situation where the weight is way more than the drag, at that situation there would be a higher resultant force downwards. So a higher resultant force downwards means that there will be a higher acceleration downwards. So a higher acceleration means that acceleration is change in velocity by time. So this means that a higher acceleration downwards would mean that the velocity upwards is greater, and since velocity is equals to distance by time, it means that higher distance will be covered at the same time, right? A higher distance will be covered at the same time, or a higher velocity means that same distance will be covered at a lower time, right? Since when the velocity is higher, then lower time will be required to travel the same distance. So basically we will have a higher weight. Since w equals to mg, a higher mass would have higher weight. A higher weight would have higher acceleration. Higher acceleration would have higher velocity, and higher velocity would have lower time. So we will need greater mass. And since I have told you that weight and drag up, right? So basically we will need higher weight and lower drag. To lower the drag, do we need a smaller diameter or larger diameter? We will need a smaller diameter. This is because a smaller diameter means that there is a smaller radius. Smaller radius means that there is a smaller drag force. Since there is a smaller drag force, the drag force would be smaller, so the resultant force downwards would be greater. Since the resultant force downward is greater, same explanation again, resultant force downwards greater, drag lower, force downwards greater, force greater, acceleration greater, velocity greater, so same distance is being covered in a lesser time. So we will need a greater mass and the smaller diameter. So the only option is C. That was the end of the paper. If you found this video helpful, consider liking and subscribing. It's just YouTube algorithm, this really helps. And good luck for your exams. Take care.